We've talked about using scientific notation for a couple of reasons. One reason is for significant figures, it's a lot more clear. And another reason is going to be important as we go on and we start looking at some actual chemistry, because right now we've just been looking at general information that'll help us out when we start talking about chemistry, especially when we start looking at moles and atoms. It's going to be really small numbers or really big numbers that we'll be working with. So scientific notation is really useful for that as well. Because seeing 6 zeros in a row can get confusing. So having it in scientific notation is much more clear. So scientific notation is written as c times 10 to the n, where c is a coefficient between 1 and 9. It can have decimal places. And n is an exponent indicating the number of tens places applying to the coefficient. A positive coefficient indicates a number greater than 1, so a big number, and a negative coefficient indicates a number less or between 0 and 1, so a small number. So that tells us which way we have to move the decimal place. And remember, we only show significant figures in the coefficients, so that makes it a lot easier to determine the significant figures, and we know all zeros, all numbers in our C is going to be significant, so that really makes it much more clear, and it's really useful. Now on the quiz, I don't know how to make Moodle allow you to put in scientific notation, so none of the ones that weren't multiple choice answer was actually needed to be in scientific notation. I won't give Moodle quizzes very often, but if, for instance, we have an issue like we did, I might put a Moodle quiz. Typically, I won't use them, but it's useful when something like Wednesday occurred. So we're going to start with this question, which was one on your quiz. I'm going to pass on the roll one more time. I don't get good results with the roll. I don't think half of everyone gets to sign it. Which is why I typically forget to pass it. But I'm usually going to be using your iClicker questions. Yep, so all you got to do, press the letter, says you a check mark, and it says it's sent. And you can change it until the time runs out. As far as uncertainty, where does uncertainty come from in measurements? And we talked about this a little bit on Monday, and it really often will come from limitations of the instrument. So in your experimental design, when you start learning how to set up experiments and you get better at it, you start learning what's the best instrument to use for the sensitivity you need. For instance, you wouldn't use a volumetric flask that's only in milliliters if you're trying to measure microliters, because it's not going to give you a very precise measurement, because it's just not set up for that value. So that's oftentimes going to be your limitations. Sometimes you won't be able to get an instrument that's as certain as you'd like. So you always need to understand your measurement, whatever you're using, whatever instrument, whether it's a volumetric flask, whether it's using something like a very expensive big instrument to determine something like gas chromatogram, mass spectroscopy, which if you've ever watched a crime show in a crime lab, they're always showing that one. What your limitations are with measurements like that. What your limitations are when you're thinking about combustion analysis, which we'll talk about later on in the semester. So it's always important to understand that. And then we also need to understand our difference between accuracy and precision. So accuracy is how close is our measured value to the actual value of the quantity. So that's just our accuracy. If I measure out and give you a sample of 5 grams of sugar dissolved in water, and I tell you to determine how much sugar is in that water, and you do whatever you do to determine it, and you come out with 3 grams, you're not very accurate. So that's our accuracy. Precision is an indication of how close repeated measurements are to each other, how reproducible that measurement is. So we'll look at both of those. So as far as precision, imprecision in measurements is caused by random errors. Oftentimes that results from fluctuations, and sometimes there's no specific cause, and maybe that instrument you're using isn't the best instrument for that. And sometimes it could also be based on human error, but oftentimes it's based on random errors. So maybe your instrument is broken, so you take multiple measurements and you're getting all kinds of different measurements. And then you take some other sample and you do it and you start getting all kinds of different measurements. Well, maybe your instrument is broken. Maybe you need to consider repairing it or getting a new one. And sometimes you can see those. Another example, if I am taking a mass of something and it's a really small mass, oftentimes you'll see a balance will have doors with a glass box around it. And that's because the airflow can, as it's going through, affect your measurement, and you can get jumping up and down, especially with really small measurements. So you want to close the doors to prevent that airflow from going in and affecting your measurement. That's another example where maybe you took the measurement with the door open, and maybe you took the measurement with the door closed, so you might not have very good precision. There's always going to be some random error, but random errors are nice because with enough measurements, they usually average out, which is why it's common to at least take 3 measurements of something, especially when you're reporting data. In biology, for example, if I'm doing some sort of work with cells and I'm trying to see how much of my substance is being uptaken by cells, I'll probably do at least 3 rounds to see how my measurements agree with each other. I might do more if I see I have some imprecision there. So we might do 4. So you often won't see 1 measurement, but you'll see an average of it. And then that's when you start looking at things like statistics. And we're not really going to be getting too much into that in this class, but things like your standard deviation and your averages when you're averaging out measurements to see how off those measurements are to each other. Now, accuracy is often caused by systematic errors. So, for example, your instrument might not be calibrated. You might take this measurement 5 times, and it's always coming out to roughly the same number, but that number is not close to the actual value. And that might be because your instrument just needs to be calibrated. So your instrument's fine, you're going to have some random error for precision, but you're not near the actual value because you didn't calibrate the instrument. So if I would step on a scale and it's not calibrated, it's not going to give me my accurate weight. So we can determine that by evaluating how far off from the actual value it is. Now, of course, the best data you want to be both accurate and precise. And data that is neither accurate or precise is not very useful. But we usually want to try to get both. Techniques can affect your accuracy, so you can reduce your inaccuracy by better instruments. Again, your inaccuracy might be caused by not using the correct instrument. If you're trying to measure something in liters, you don't want to use a microliter instrument. That's going to, 1, take a lot of time, but 2, you're going to have issues there. So using the correct size instrument. Now, our systematic errors do not average out with repeated measurements, which is why you might take 5 measurements. They're all not accurate, but they're all precise, close to each other, because your instrument just isn't calibrated. So they don't average out, and you need to actually change something you're doing to fix your accuracy. Whether it's calibrating your instrument, using a better instrument for what you're trying to do, your technique. So if I'm doing something in the biology lab where I'm having to add a certain amount of different chemicals to cells, I want to make sure I'm doing that the same every time I'm doing it. So if my technique isn't correct, I'm going to get bad results because I'm not following the correct technique every time, or I'm being sloppy with what I'm doing. So if we look at this example, student A, student B, and student C, in this case we're determining the mass of an object. We can say some things about student A, B, and C's accuracy and precision. Sometimes looking at it like this isn't as easy to tell, so we might use some sort of graph to visualize this data in a more comparable way. So looking at that, if we know the known mass is 10 grams, and we look at student A's numbers, we can see that it's not very accurate, depending on what we consider accurate. So it's off. And we can also say it's not very precise. They're getting numbers kind of all over the board. Versus, we can look at student B. Student B is getting about the same measurement for all 4 measurements, but it's not accurate. So it's precise, but it's inaccurate. Student B, while student A might be using sloppy technique, they might not be letting their instrument equilibrate before they write down their numbers. So you know how when you step on a scale and then it jumps up and then it goes back down and then finally gets to your, maybe they took the measurement right away. So maybe they were sloppy there. But student B might just have an uncalibrated instrument. So they're getting the same number, but it's not accurate, whereas student C is completely accurate and precise. So their instrument is proper for what they're doing, it's calibrated, and it's getting close to where their value should be. Again, you're never going to have 4 of the same number, and if you do report 4 of the same number for 4 different trials, I will question you. Because, again, there's always going to be some error, even when we have something that's accurate and precise. It might not be a lot of error, but it's always some. So looking at this one, and even though the number was slightly different on the quiz, what we can say is that the data is, in this case, we're seeing that it's very precise, but it's not very accurate because it's still off by a decent amount. This is, again, look at all the significant figures we have. Don't just go by 2.5. Look how we're all the way down to this number. So we have less of error because we have a lot more significance. Our instrument can measure a lot more sensitively. So the amount of how accurate something is also dependent on the amount of significant figures you have. And we'll be talking about that a little bit as we go on. But now I want to move to generally solving problems. And again, we're going to be applying this to chemistry problems. Right now, we're just thinking about how we should approach specifically word problems are what we'll be seeing a lot of. So if we're solving problems, the first thing I want you to always do is follow your units. And it's going to seem tedious sometimes, but it'll really help you to map out what you're doing and see if you made a mistake, if you're following your units. And it's pretty clear when you're not following your units, or when I'm grading you and I see you don't write down units and then you get the wrong thing, it's easy, I can see why you got lost. Because you're not following your units. So following your units will be really useful, even though sometimes it seems tedious. Even not just following your units, but your units of what? For example, if I'm measuring out a certain amount of a drug to give to a patient, and I'm told that the patient gets 25 milligrams per kilogram body weight. Milligrams and kilograms, that's both mass. But what I'm talking about is 25 milligrams of the drug per kilogram body weight. So when I write that, I want to write milligram drug, kilogram body weight. Because what's going to cancel out? The body weight of the person and the kilogram body weight on the bottom. You can't cancel out milligram drug and milligram body weight. That's not the same thing. I am not a drug. So even if we're in the same type of units, in this case mass, we still want to know what we're talking about. And we'll see that in chemistry because we will be looking at figuring out theoretical yield. So we'll need to know, okay, if I have this amount of sodium hydroxide in moles, how many moles of potassium hydroxide will I form? So that's two different things, even though they're both in moles. So even though not just following your units, but following your units of what is going to be really important. So we want to write every number with its associated unit, and if it's appropriate, what it is. So you can do the same thing with operations as you do with numbers. Centimeters times centimeters equals centimeters squared. Of course, centimeters plus centimeters still just going to equal to centimeters. That would just be, we have 1 centimeter plus 1 centimeter, that would give us 2 centimeters. So adding. Same thing with subtracting. 2 centimeters minus 1 centimeter is going to give us 1 centimeter. The unit's still centimeters. Remember, we can only add and subtract like units, so we can't add 1 meter to 1 centimeter. We have to convert one or the other. If we divide a centimeter by a centimeter, we get 1. We no longer have a unit. And that's how we're going to be using for our unit analysis, which we talked about briefly, but now we're going to be applying it more. So using our units as a guide to problem solving is what we call dimensional analysis. And it's really, really useful, especially to keep yourself from getting lost. So we already talked a little bit about some relationships, like density. We talked about some relationships like how many milliliters equal to a liter, that's relationships. So when we're looking at relationships, they can be used as conversion factors. And again, you want to make sure that you're writing down your units. So for example, 1 inch is equal to 2.54 centimeters. So we can write that as either 2.54 centimeters over 1 inch, or 1 inch equals over 2.54 centimeters. Both cases, we're seeing 1 inch equals 2.54 centimeters. And we can use that as conversions factors. But to use this as dimensional analysis, we want our units to cancel out. So whatever unit is on the top, we're going to put that same unit on the bottom in our relationship. So we can use this as a string as well, as long as we have units that are related to each other. So if we have a relationship, find unit equals given unit, we want our given unit on the bottom so it can cancel out. Because remember, centimeters divided by centimeters equals 1. So that's what we're doing. And then you can do a string as long as you have a relationship that relates different units. And I'm going to be showing actual examples with this because for me, examples mean more than just reading this. So this is the theory, but I'm going to show the actual examples. So for example, let's say we have a given unit, and then we say given unit equals related unit. And then we have another relationship between this related unit and whatever unit we're trying to find. So we can draw a string. Our given units cancel out. Now our answer would be in related units. But we don't have to know what that number is. We can then put our related units on the bottom, cancel those out, and then what we're left with is our answer in our actual found units. You can technically find this number and then take it and go on. But remember, if you do that in steps like that, don't round until you get to the end. Otherwise, you're going to lose numbers, especially when we're talking about our significant figures. So it's easier just to go all the way through because we're not going to round until we get to the end anyway. But in theory, if you did this step, found an answer, then did this step, you'll get the same answer, as long as you're not losing your numbers in the way or writing them down incorrectly. So you always want to be careful you're writing numbers down correctly. Don't worry, I'm going to give some actual examples to this beyond just find unit. What can help you, and this is the way I'll typically teach in here, it doesn't mean you have to, you might not need to do that, but as far as me teaching, especially in students being able to look back, I know I have to go fast in class. I got to get you to a certain point for you to be able to do 106. I have to because 106 starts at a certain point. If we don't get there, you got to learn it on your own. I don't want to do that. So I have to go fast. I'm giving you all these tools where you can go ahead and listen to me talk for another hour on your own and pause things when I'm going through it. So I am going to do it, and I always do my work on the computer so they will show on the videos. But I'm going to teach this as a conceptual plan. This is just a visual outline for our strategy to solve problems. It's going to seem a bit tedious at first for easy problems, bless you, but it really helps later on. And again, you don't necessarily have to go through a conceptual plan, but that's the way I'm going to teach it so everyone in the class can follow me. So what our unit conversions will focus on our units and how to convert and what relationships we know. With equations, our conceptual plan will typically focus on our equation. So fairly simple. So for example, if we want to convert inches to centimeters, first I have to find a relationship. Do I have a relationship between inches and centimeters? Here's one. 1 inch equals 2.54 centimeters. So I have that relationship. So my plan would be, I want to take inches to centimeters. And if inches are at the top, then that means that my conceptual plan will put my inches at the bottom so it can cancel out. Again, seems a little easy when we're just doing one simple conversion, but as it gets more complicated, this will help. Not something you necessarily have to do, but it can help you if you're having problems. So this is just a systematic approach. And I'm a scientist, so I like systematic approaches because that's how I come up with experimentation. So that's how I always will go at a math problem. It helps me to sort the information and also helps me to find relationships. So I'm going to first always figure out what I'm given in a problem and what I need to find. And then I'm going to write a conceptual plan to find that. And sometimes I might work backwards. Sometimes it might involve the conversion factor and equation. And sometimes I'm going to teach it in a way that maybe seems harder to you than it needs to be because everyone thinks a little bit differently. But again, remember, I'm trying to teach it in a way where everyone in the class can follow it. That's my goal. That doesn't even mean that if I were to take the problem on my own, that I'd necessarily do it that way. Which is why when I go through problems, I have worked most of the homework problems, so I know how I want to explain it. Because otherwise, I just start writing things down, and I don't want to go too fast. Because I find that the easier something is for you, the harder it is to teach it. So applying these steps, and then you always want to think a little bit about checking your answer. What you know, does it make sense? Using a little bit of common sense about what you know about chemistry to figure things out. Does this make sense? I know, for example, that milliliters are smaller than liters. So if I'm converting liters to milliliters, I should have a bigger number. I know that. So I should check that just with my final answer because I know some things already. So those kinds of things can help you avoid mistakes for double checking your answers. So let's look at this first example, which was of course one on the quiz. So we are converting a certain amount of yards to centimeters. So our first step is, what are we given? We are given 1.76 yards. So what we're given. And I want to write that unit, and we want to find that number in centimeters. So again, you don't necessarily have to memorize these. I would give them to you if they're important. But looking at this table, I see that I don't directly have a conversion from yards to centimeters directly, but I do have a conversion that .094 yards equals to 1 meter, and I know that 1 meter equals to 100 centimeters. And again, you do need to know those conversions. So I don't just have one relationship, but I have multiple relationships. In this case, sometimes you will have one. So my conceptual plan will take my yard, and I don't have a direct conversion to yards to centimeters, so I'll convert it to my meters. And then I'll be able to convert that to centimeters. So that's my conceptual plan, how I'm going to do it. So looking at my solution, starting with 1.76 yards, and yards are at the top. So I'm going to need, for my conversion factor, which is 1.094 yards equals 1 meter, I'm going to need that 1.094 at the bottom. And my 1 meter at the top. So my yards do in fact cancel out. That makes sense as far as that's concerned. Now that means that if I figured out this number, it would be in meters, but I want it in centimeters. So my meters, 1 meter is going to go at the bottom, and my relationship is 1 meter equals to 100 centimeters. So now my meters cancel out. I'm left with centimeters at the top, and that's my desired unit. So I set this up correctly. If you can't cancel out, you set it up incorrectly. Also remember, don't switch. Don't say 1 yard equals 1.094 meters. You cannot do that. Yes?
I remember I feel like this, I can't like I'm not sure if I can describe it or it's like a walrus. But I heard instead of like doing this, I convert yards to inches and
You can do that. You can do yards to inches. You can use multiple relationships that are in agreement and come out with the correct answer, as long as you have a way to get from inches to centimeters. If you have a relationship between yards to inches and then a relationship between inches to centimeters, that's perfectly okay. I'm showing one route that doesn't mean that that's the only route. And in this particular case, you could use, because we have it here, you could use yards to inches on here. Yards to inches isn't on this particular one. You could look it up, because I'm sure there's a conversion somewhere. But let's say I give you a test, this doesn't have yards to inches, so you probably wouldn't do that. But there are multiple routes, because we do have a route from inches to centimeters. So it really depends on what your relationships that you have available to you are. But there are multiple routes that would give you the correct answer. So using the givens that I had, I can calculate this one, and of course everything on the top is multiplied, everything on the bottom is divided, and when I do that, I will get this number, but the correct significant figures. Remember, this is a relationship, and it's an exact number, and that's an exact number, so they're infinite. So we started with 3 significant figures. We are multiplying and dividing, so our final answer should be in 3 significant figures, which is 161 centimeters. Oops. And as far as checking, based on what we know about yards and centimeters, we know yards are much bigger than centimeters, so it makes sense that centimeters would be a larger number, because we know that about those measurements. Now what if, like I said, if we cube centimeters, we'll get cubic centimeters. Do we need specifically different relationships when we're looking at cube relationships? And the answer is not necessarily. So if we're having units and we're raising them to powers, we can still work with that. So let's look at this example. We're converting cubic inches to cubic centimeters. Well, our relationship is 1 inch equals to 2.54 centimeters. But we're relating cubic inches to cubic centimeters. So that means we have to raise that whole relationship to the power of 3. Now we know 1 raised to the power of 3 is still going to be 1, but don't make the mistake. 2.54 raised to the power of 3 is not 2.54. So we have to cube that entire relationship, so that way we can cancel out cubic inches. We cannot cancel out cubic inches by inches. Remember, if we divide inches, let's put it here, inches cubed by inches, we're going to end up with inches squared. So for that to fully cancel out, we need to divide it by inches cubed. Otherwise, we're not going to fully cancel out. So we can do that, but we have to cube the entire relationship. So writing our conceptual plan, inches cubed to centimeters cubed, we're going to be using this relationship, but we're going to cube the entire thing. And again, don't make the mistake of centimeters cubed without cubing the number. Because you are cubing the number, which would be 16.4. So make sure that you cube the entire relationship. Of course, 1 is cubed because that's just 1. But don't make that mistake. You cannot just make this relationship cubed and not cube the numbers, the coefficients. So let's look at an example. Again, this was from the quiz. 5.70 liters to cubic inches. So we're given 5.70 liters, and we want to know, oh, it's already in there, volume in inches cubed. So our conceptual plan, we can take our liters to milliliters, and then remember our milliliters, and we can convert that really easily to centimeters cubed, because our 1 milliliter equals 1 centimeters cubed, which is a really nice conversion to have. And then our centimeters cubed can be converted to inches cubed. And of course, our relationships for what we're looking at, our 1 milliliter equals 1 centimeters cubed. Again, that's one you should know because you see it so often. You know that they're interchangeable. Our 1 milliliter and how it's related to liters, and we know how our inches and centimeters cubed are related. In centimeters. And again, you don't have to memorize how your inches and centimeters are related. Because, again, that's something you can look up. So our solution to putting this in, we're starting with 5.70 liters. Our first relationship we're going to want to use is how our liters relates to our milliliters, because that's our given unit is liters. Again, I like using 1 liter equals to 1,000 milliliters, which is the same thing that this relationship is showing. Either way you do it, you're going to come out to the same thing. So that means I can cancel out my liters. Now, if I figured out that number would be in milliliters, but that's not what I want my final thing in. So I can convert that to centimeters cubed, which you should know that relationship. So my milliliters is going to go on the bottom, and my centimeters cubed on the top. When you start doing a string like this, you can see how easy it is to get lost if you're not following your units. So really make sure to write them down, even though it might seem tedious. Again, we're taking our 2.54 centimeters, which is going to be at the bottom, and we want to take that to our inches, which is going to be at the top. But if I divide centimeters cubed by centimeters, I'm just going to still have centimeters squared. So I have to cube my entire relationship. That way it can cancel out. So I'm going to rewrite that. You can do it in your calculator. You don't necessarily have to rewrite it, but so you can follow it later. And again, if we were working with centimeters squared, we'd square the entire relationship. So depending on what you're doing. So when we do put this in our calculator, again, everything at the top is multiplied, everything at the bottom is divided. We get 347.83. I don't know why I put my decimal place there. inches cubed. Of course, I started out with 3 significant figures, and my relationships are all exact numbers, so they're not going to contribute to my significant figures, so my final answer should be in 3 significant figures. And that makes sense based on what we know about how liters and inches are in agreement. Again, following your units can really help here. And the biggest mistake, again, that I see when we're doing this, where our units or our relationships having to be taken to an exponent, is not doing that to the coefficient. So you can't just leave 2.54. You have to cube the entire relationship, or squared, or whatever you're doing. So for the example, let's look at another example. And here we have a dolphin swims at an average of, clearly this is in chemistry, pace of 15 miles per hour. How long will it take for the dolphin to travel a certain amount of feet? And I have some relationships. So first off, 2 relationships are in parentheses. 1 mile is equal to 5,280 feet, and 60 minutes equals to 1 hour, which is probably not one I had to give you, but it's one nevertheless. However, this example gives you another relationship for that specific dolphin. And they notice that this relationship isn't a known relationship or an exact value, but a measured relationship, which means those significant figures can contribute to your total significant figures because it's a measured relationship. Not all dolphins necessarily. Or what happened was the scientists went and measured the dolphins and got an average of 15 miles per hour. So that's a measured relationship and doesn't necessarily have significant, exponential significant figures. So always pay attention. Same thing with density. Density is a measured relationship. So measured relationships, they do have significant figures because someone had to measure that. So we're given a certain distance, which is 3,500 feet. We're also given a relationship, and that is for this dolphin, or for this dolphins in general, the average is 15 miles per hour, which means for every hour, the average dolphin will swim 15 miles. So that's a relationship given to us in this equation. So it's important to recognize when relationships are given to you and when they're measured relationships. And then, of course, these other 2 relationships are known relationships you could look up. So our conceptual plan, we're going from feet to miles, because we know 1 mile is equal to 5,280 feet. Then we know how many miles per hour our dolphin swims, so we can convert that to hours. But this wants to know in minutes, apparently, so we can convert that to minutes. I think this was a multiple choice one. So all the multiple choice ones were given to you in minutes. Clearly, we had to convert it to minutes. So that's our conceptual plan. We're starting out with 3,500 feet. And feet are going to go at the bottom. And that equals to 1 mile. My feet can cancel out. Then I have my relationship that was given to me in the problem. This relationship would be different if I was talking about a cheetah swimming. So that's a specific relationship. And my 15 miles goes at the bottom because miles cancel out. And my 1 hour goes at the top. And then lastly, to convert it to minutes, my hour and my 60 minutes. My hour is going to be at the bottom. That cancels out, and I'm left with minutes. So then I just calculate this. then when I do that calculation, I get 2.65 minutes. But remember, here, significance, as far as what's significant, this is a measured relationship of 15 miles, and that only has two significant figures. And my given only has two significant figures. It's not real clear if these zeros are significant, so I'm going to assume that they're not. So, I have two significant figures, and that's what my final answer should be in. Before I go on to density as a conversion factor, I just want to reiterate what I was saying. Come on. Why don't you do it? There we go. Let's say and remember, I do upload this. Let's say I have a person, they weigh 160 kilograms, and I want to give them a dose of 25 milligrams per kilogram of a certain drug. How much drug am I given? How many milligrams? Again, here it's really important to understand your relationship. I'm talking about a 160 kilogram person. And what my relationship is telling me, for every 25 milligrams, or I need to give 25 milligrams of our drug for every 1 kilogram of body weight. So when I'm doing this conversion, it's also important, and it gets really confusing. Let me make it really confusing. This is a lot of drug. So this isn't, you're not going to see it, but I still just want you to understand it. Let's say 0.5 kilograms per kilogram body weight. Because you would normally say I can cancel out kilograms. But you can't, because what this is saying is you're giving 0.5 kilograms of the drug for every kilogram body weight. So those two are not the same thing. That's why I changed it on you. Because I want it to be really clear. So when I'm starting my relationship, I am converting my kilograms of body weight to my kilogram of drug. And then, of course, you convert that to milligram after. So let's just say we're looking for it in kilograms. I'm sorry? This is kilograms, so it's K. 0.5 kilograms per kilogram body weight. And that's usually how it's given. It's not given in kilograms body weight per kilograms drug. It's kilogram per kilogram, and you're to understand it's kilogram drug per kilogram body weight. So that's something that's typical. You won't typically see it like this, which is why I want you to understand that these two things aren't the same. So when we're doing this calculation, 160 kilograms, I want to write not just kilograms, but I want to also write body weight. Because my relationship is this. So when I'm coming here and trying to figure out what part of my relationship can be canceled out, I can't cancel out kilogram body weight by kilogram drug. So what has to go at the bottom? The kilogram body weight. Because that's my relationship, and those two things are not the same. And that's probably a lot of kilograms of drug. So it's just to show a point. So my 0.5 that is with my kilogram drug goes on the top. So I can cancel out kilogram body weight and kilogram body weight, but I can't cancel out kilogram drug and kilogram body weight. Later on, when we're going to do moles of something in a reaction converting to something else in the reaction, this is going to be really important. So I want you to understand that sometimes you have to be more specific than just units. And we're going to see that later on. So I wanted to show that. So the last thing that we're going to be looking at today is density as a conversion factor. Now remember, our density is our relationship between mass and volume. So that is a relationship. It is specific to certain things. Water has a certain density, lead has a certain density, and of course we do need to know, for example, densities at certain temperatures, which will be important later on. So all of these. Now remember, I still have 5 minutes, so you shouldn't leave until I'm done talking, and I will never go over, but we don't end for another 5 minutes. And I will teach until the end of class. And I'd really appreciate it if you don't start moving early because it creates a distraction. So what we're looking at here is a relationship. If density of water at room temperature is 1.0 grams per milliliter, that means for every 1 gram of water, I have 1 milliliter of water. And again, here's where it's really important. I want to write grams H2O and not just grams equals 1 milliliter. Because that's not true for every substance. It's true for water. Whereas lead, I have 11.3 grams of lead for every 1 centimeters cubed lead. I don't want to write 11.3 grams equals 1 centimeter cubed. I want to be specific that it's lead, because later on that's going to be really important. So these are conversion factors. If I'm looking at this, if I have a certain, in this case mass, 4.0 centimeters cubed of lead, if I know my density of lead at that certain temperature, I can calculate what that mass is, because I have the value. I have 4.0 centimeters cubed. I have it. So I can set up my relationship. I would have my centimeters cubed lead on the bottom. That can cancel out. And I have my 11.3 grams of lead on the top, because that's my relationship. Again, notice I am writing PB, because I want to be clear that that's only the relationship for lead. That's not the relationship for anything else. So here I get 45.2 grams of lead. Now remember, this is measured. We can measure this. So that will and can contribute to my significant figures, but we have 2 significant figures here. Here we have 3, so our final answer will be in 2, because we're multiplying and dividing. So that's 45 grams of lead. So looking at our example from the quiz, and this is the last thing I will go over today, we're looking at 100.0 grams of marble, and we're giving our density of marble, which would have to be given to you. You don't have to memorize densities, with the exception of water, because we'll see that one a lot. But I'll give it to you. I don't expect you to know the density of marble. So our relationship is 4.0 grams of marble equals 1 centimeter cube of marble. So if we want to know that volume, that's fairly straightforward to figure out, because we have that relationship. So we have it in grams. Now you do have to be careful. I could give you the mass of marble in milligrams, so you might have to convert that to grams first. In this case, we don't have to do that. We have 100.0 grams of marble. So our 4.0 grams is going to go on the bottom. And my 1 centimeter cube of marble at the top. And that can be canceled out. So that will give us our answer. And that should be our answer in 2 significant figures because 4.0 is in 2 significant figures. Okay, so you guys remember, no class Monday. We are off. And my tentative schedule shows all the holidays y'all have. I haven't heard anything about any hurricane days being taken away from fall break. So that's what fall breaks are for, hurricane days. But I haven't heard anything yet. So I'll let you know if I hear anything. As of now, I haven't. So I will update that when it's appropriate. You guys have a great weekend. And the